I'm going to add a few general points from another book here before we move to the third chapter on the evolution of behavior. This book, Climate Changes in the Holocene, Impacts and Human Adaptation, focuses on slightly different things, on how technologies for water, etc., were innovated by our ancestors during, let's say, the Holocene, and how some survived, some didn't survive, and it also gets a little into geoengineering and how we are trying to adapt to what may come in the future because of our impacts on greenhouse gases and global warming. So it's called Climate Changes in the Holocene, Impacts and Human Adaptation, but it has few points that I wanted to pick up which seem appropriate at this stage before we move on to more details on climate and human impacts. So we will look at details of climate change along the way, of course, but this figure is nice, which is showing a deep ocean temperature for a longer period here, going from the Pliocene into the Pleistocene, and this Pliocene boundary always comes up in discussions on human evolution because this is where the potentially the Indonesian Seaway connection between the Pacific and the Indian Ocean changed, Australia and New Guinea moving north and blocking the direct connection, changing the El Nino dynamics. We will learn a little bit about El Nino, but I also have podcasts elsewhere that you can look up if you don't know what that is. Essentially, that then ended up creating what is called East African aridification, which we will discuss in much more detail, and is argued to be one of the most important climate impacts on evolution in terms of going from quadrupedalism of our primate relatives to bipedalism, which changed a lot of things anatomically, and then also allowed the cranium to grow, brain size to grow, and so on and so forth. So we'll come to these things as we go along. So 5.33 million years ago, you can see that there is also a change in the time scale. There is more of a precession time scale, 21,000 years, and obliquity time scales of 41,000 years, and then in the Pleistocene we slowly transitioned into these 100,000 year ice age cycles, which are zoomed in here for the past 800,000 years. And you can see that this was a warm period, and then we got into this unstable climate. So the question of whether climate stability is more important for evolution or climate variability drives innovation in evolution as well is a question, especially when we come to the Holocene. We will see later on that Holocene is a relatively stable period where agriculture became possible and changed our way of living, and as sapiens we are the only species remaining into the Holocene. So whether this stability was important for our evolution, or we ourselves changed climate in a way that we made it more stable. So these are interesting questions, but we will discuss more details about we'll mention Holocenian warm period. We will look at the period here going from the Eemian 135,000 years ago or so through the various marine isotope stages to the end of the last ice age around 10,000 years ago, and warming back into the Holocene. Okay, so this is a nice figure that kind of shows this in a good way. And we'll also see along the way this idea of whether climate perturbation is always been a driver. It's called environmental determinism. Not everybody believes in it. There is strong wind again here, so hopefully the recording is okay. I will check and make sure. It leaves this horrendous noise in the sound, which forces me to re-record by closing the windows. But anyway, so the environmental determinism tends to imply that climate change, climate impacts tend to be very critical in critical junctures, at key junctures of evolution of speciation and out of Africa, and species succession, and so on and so forth. So obviously one of the key forcings when we go before humans became so dominant in impacting greenhouse gases and climate change. We don't know whether we started having impact already here. We will see some arguments from Bill Ruddiman saying that we have been impacting climate throughout the Holocene. But insolation changes have been critical, and there are critical latitudes where we look at these changes. This is the Milankovitch cycle, which we'll come back to. But from the last glacial maximum around 21,000 years ago, we started to warm. We've had Heinrich events, Bowling alley rods, Younger Dryas. We will look at these things. But the insolation forcing went up at 50 north in July, which led to wetter climate. So Ethiopian African monsoon maximum began to pick up, and then as the insolation forcing turned down, we slowly got into arid periods, and there are civilizational impacts recorded during these times. Greening of Africa is a big one, and we will look at those things. When we look at paleoclimate, we also do these things where we look at forcings, let's say from obliquity and from eccentricity and precession and so on. So this is caloric summer insolation anomaly to the present period, going from 800,000 years ago, and this one also goes into the future. Basically, the Milankovitch cycles, which we'll discuss in a bit more detail, allows us to calculate solar or orbital changes in terms of ellipticity, obliquity, and precession back and forth for any number of years. But the internal feedbacks, the ice albedo feedback, water vapor feedback, cloud feedbacks, vegetation feedbacks, lapse rate feedbacks, and so on, produce multiple time scales, and this shows it nicely. We will discuss a little bit about the proxies we use to estimate the changes in the past, like the benthic delta O18 that is shown here, and CO2 concentration that is derived from the bubbles in the ice core from Vostok, where this data comes from. But the main point I want to point to is that we have this 100,000 year cycle in temperature, which is delta O18 is a proxy for temperature, and CO2, and we will look at details about how temperature leads when the orbital forcing is creating climate change, and CO2 follows, and we will talk about abrupt changes versus slow changes and so on. But the main point is that there are many insolation maxima here, but they are not necessarily showing up as peaks here. So some of them do and some of them don't, and in fact some of them don't match the peaks in insolation and so on. So internal feedbacks can select multiple time scales. Especially we will look at marine isotope stages in some detail here in the last 135,000 years, and that'll give you a better sense of what we are talking about. Of course, it in the end comes down to what role climate may have played, or what role behavioral evolution, brain size increase, natural tendencies to explore and so on would have combined to produce these kind of dispersals of hominids throughout the world, and the approximate time of arrival in various regions are shown here. So we start here using genetic clock methodologies. We can say where the origin most likely occurred 3.6 million years ago. We'll discuss many other issues about other species, whether they evolved independently or all kind of migrated out of Africa and so on and so forth. So many issues remain unresolved, but nonetheless you can see here this is much more recent, 120,000 years ago, but you have sites much older, 1.5 million years ago here, and 700,000 years ago. And these evidences also keep changing with new findings, archaeological evidences or other fossil evidences and so on. And there are other issues as to why Europe has much more recent arrivals than some places here in Asia, for example, 600,000 years ago here, 1.8 million years ago here, and of course crossing of the Beringia into the New World much more recently from 12,000 years to more recent times in the Holocene, and so on. So many interesting issues here. So 700,000 years ago here. So how these migrations happened, of course, over these kind of time scales, sea levels have changed a lot. Aridification, drying, wetting, warm, cold periods, and so on have occurred. So we have to look at all those things, but this is just an idea to give you broadly what issues we'll be discussing. And this is a nice framework to think about how we have adjusted and how we are planning to adjust for the future with increasing greenhouse gases and global warming. The resilience cube illustrating the three resilience capacities: adaptive, absorptive, and transformative, in relation to the three phases of transition. So nature with human, nature for human, and human and nature. So when absorptive capacity, transformative capacity, and adaptive capacities are low, you are in a very vulnerable stage. If adaptive capacity is high, then you have this so-called nature with human happening. So absorptive capacity is still low, but as absorptive capacity increases, nature for human kind of adaptation can occur. So phases of transition can occur, and if adaptive capacity is high and transformative capacity is high, then we are at the current stage where we are using technology and science to feel almost invulnerable to climate change. But this, of course, can be dangerous if we are not careful, because somebody is paying a price. Not everybody has the same adaptive capacity, not everybody has the same absorptive capacity, not all countries, for example, have transformative capacity, and so on. So if we continue in that sense, where we have high adaptive capacity, high absorptive capacity, and high transformative capacity, then we reach the most resilient stage where the human and nature can coexist. In other words, nature doesn't really care. We can kick it and it'll do something which may not be good for us. So nature is not going anywhere, planet is not going anywhere, and biology is not going anywhere. Somebody will survive. It's a question of who survives and what will happen to us as a species, right? So these are the kind of issues we have to worry about, and we will talk about the future in the last chapter of the book as we conclude the course. So I hope this gives you kind of a lay of land in terms of the various issues we'll be discussing as we go along in this course. Okay?